All right. Um, Hello, classes. Uh, I I think I'm going to take tomorrow off to write some letters of recommendation because I'm realizing that I have quite a few November 1st deadlines. So I thought I would just record my lessons right now, and then I can just focus on that tomorrow. So I'm going to be recording a lesson for my IB physics class, my CHL class, um, and my computer science class. Um, and so I'm just going to start with the CHL. And you guys are, for CHL, you guys are going to do Momentum Quiz 1 tomorrow. And so we're going to be introducing momentum today. All right. I will have, I think, a double length office hours on Tuesday to make up for the no office hours tomorrow. Okay. Do fill out your attendance as you would normally, because I will submit the attendance. I'll be doing that as usual. Okay. So today we're going to talk about momentum. Which is denoted by p, lowercase p. It's a vector, and it is equal to the mass of the object times the velocity of the object. Okay, so it's a very simple equation. Notice that this is a scalar multiplication, mass times velocity, scalar, and this is so we can use this to determine the units of momentum. Okay, so the units of momentum are going to be units of mass times units of velocity. So that would be kilograms times meters per second. Kilogram meters per second. Another thing I wanted to say is that this is the general form of momentum in 3 dimensions or 2 dimensions. We have to use vectors. But if we have something that's just moving in 1 dimension, which is going to kind of be the topic of today's lesson, then you don't really need to use vectors. You can just say P equals M times V without the vector arrows. Okay? So what I would like to do, first of all, is actually take the formula for momentum, and let's take the derivative of the formula for momentum with respect to time. Okay, so so we're taking the derivative of the momentum formula with respect to time. Now, notice that the mass of the particle is going to be a constant. Okay, so when we take the derivative, we don't need to take the derivative of the mass. We only take the derivative of the velocity. Okay, so we have m times dv dt equals dp dt. And the derivative of the velocity with respect to time is the acceleration. Okay. And if we think about Newton's second law, which says that net force equals mass times acceleration, then that means that m times a is equal to net force. So setting the first thing equal to the last thing tells us that the net force is equal to the derivative of the particle's momentum. Okay? So there you have it. So I like to call this kind of an alternative form of Newton's second law. Alternative form of Newton's second. Okay, so we're actually going to use this alternative form to prove that momentum is conserved. Okay, so we're going to do a little theorem here, and the theorem says that. By the way, I forgot one quick thing. The total momentum of a system is defined as the vector sum of the individual momenta. Okay, so the theorem that I'm going to prove to you here is that if a system of particles has no external forces acting on it, then momentum is conserved. Okay, and so what that means is that the initial total momentum is equal to the final total momentum. Okay. Another way of saying that is that the derivative of the total momentum with respect to time is going to be equal to 0. All right. So here's the proof, and we are going to prove it for the case of n equals 3 particles. Okay. And the reason that we're going to prove it for the case of 3 particles is it's going to be obvious how this generalizes to any number of particles. It's true for any number of particles, but yeah. All right. So here's how we're going to do it. Okay. We're going to say, suppose we're going to write down Newton's second law for each of the particles, each of the 3 particles. So we have dp1 dt equals the net force on particle 1. Okay. Now, because we have 3 particles, okay, there are no external forces. This is a critical point. The only thing that can exert a force on particle 1 would be particles 2 and particles 3. Okay? So the derivative of momentum 1 with respect to time is going to equal the net force on particle 1, which is going to equal the force of particle 2 on particle 1 plus the force of particle 3 on particle 1. Okay, so we are not going to have any other terms because there's only two other things that could possibly exert a force on particle 1. All right. Similarly, the derivative of particle 2 with respect to time is going to be equal. Now, what could exert a force on particle 2 if there are no external forces acting on this system? Well, the only things that could exert a force on particle 2 are particles 3 and particles 1. So the force of particle 3 on particle 2, and then the force of particle 1 on particle 2. Okay. Now, if we look at the derivative of the third particle's momentum with respect to time, that's going to be equal to the net force on the third particle. Now, what could exert a force on the third particle? Well, since there's no external force, the only thing that could exert a force on particle 3 is particles 2 and particles 1. Okay? So there's the force of particle 1 on particle 3. And then there's the force of particle 2 on particle 3. Okay? So now what we're going to do is we're going to take these three equations and we're going to add them all together. Okay? Now if we take these and we add them all together, on the left-hand side we get the derivative of the first plus the second plus the third. So that's going to be equal, I'm going to write the answer up here just so I don't go to the other page. So on the left-hand side we're going to have the derivative of the total momentum with respect to time. Okay? On the right-hand side, adding up all of these terms, we can see that something is happening that's going to make everything cancel out. Okay? See how we have the force of 3 on 1, and then here we have the force of 1 on 3. Okay? By Newton's third law, those are equal and opposite forces. So if we add those two together, they cancel each other out. Okay? If we look at the force of 2 on 1, here is the force of 1 on 2. Those are equal and opposite forces. So those two cancel out. All right? Then if we look at this one, there's the force of particle 3 on particle 2, and then the force of particle 2 on particle 3. Those are equal and opposite forces. So they cancel out. Okay? So every term cancels out with another term, and we get that the derivative of the total momentum with respect to time is 0. Okay? So that's the proof is done. A couple of key points. It is absolutely necessary that there be no external forces acting on the system, because then there would be extra terms here that come from the external forces, and these ones might not cancel. Okay? And then the second thing I wanted to say is that momentum would not be conserved without Newton's third law. So Newton's third law is critical in having all of these terms cancel out. Okay? So the total initial momentum is equal to the total final momentum. What do we want to use momentum for? Well, momentum is used when particles collide. Okay, so why is momentum used when particles collide? Well, it's because momentum is conserved, okay, and so the momentum before the collision is equal to the momentum after, and so we can use that equation to solve problems, okay? So we're going to do a couple of examples, okay? So I'm going to do, I think, 3 examples here. First example. So the thing I want to reiterate is whenever there's a collision where 2 things smack into each other, we are going to use momentum conservation, okay? So as our first example, let's go ahead and look at what's called a completely inelastic collision. Okay. And so what we have here is we have a block. This block is starts out at rest, and it has a mass of 2 kilograms. This block has a mass of 3 kilograms, and it's headed this way at, let's say, 10 meters per second. Okay, so this one starts at rest. The 2 blocks have a collision, and when you have a completely inelastic collision, they collide and they stick together. Okay. I'll focus this again. They collide and they stick together. Okay, so after the collision, it's going to be both of these blocks together. And because they're stuck together, they're going to have the same velocity. Okay, I'll call that V sub F. All right. If they had different velocities, they would be slowly drifting apart. So let's go ahead and use momentum conservation. P initial equals P final. So before the collision, the momentum of the system is going to be mv, so 3 times 10. That's going to be the momentum of the 3 kilogram mass, plus 2 times 0, which is the momentum of the 2 kilogram mass, because it starts at rest. The final momentum is going to be the momentum of the 3 kilogram mass, which is 3 times V final, plus the final momentum of the 2 kilogram mass, which is going to be 2 V final. All right. So 3 times 10 plus 2 times 0 is 30. And then notice how, because they have the same final velocity, I'm showing this explicitly this time, but generally speaking, if 2 things collide and stick together, then I would just treat them as a single 5 kilogram mass to begin with, and I would just write it as 5 V final. Okay. So dividing both sides by 5 says that V final equals 6 meters per second. So these 2 blocks will be headed to the right at 6 meters per second after the collision. So as you might expect, the 3 kilogram one, because it hit the 2 kilogram one, it slowed down. And the 2 kilogram one, because it started at rest, it actually speeds up. Okay? Very good. So the other thing I wanted to talk about is I wanted to look at the kinetic energy before and I wanted to look at the kinetic energy after this collision. Okay. All right. So if we look at the initial kinetic energy, we start off with 1/2 times the mass. So let's calculate the initial kinetic energy of this system. We have 1/2 times the mass, which is 3 times the velocity squared, so 10 squared, plus the kinetic energy of the 2 kilogram one, which is going to be 1/2 times 2 times its initial velocity, which is 0, so 0 squared. And so we get 150 joules is the initial kinetic energy, if we simplify that. If we look at the final kinetic energy, again, treating these two masses as a single mass, we would have 1/2 times 5 times the final velocity squared, which I know is 6. All right, so I have 36 over 2, which is 18, times 5, which is what, 90 joules. Okay, so I can see that the kinetic energy, some of the kinetic energy went away. All right, so actually there was 60 joules of kinetic energy lost. Okay, so where did that kinetic energy go? Okay, it became heat. It became sound. It deformed the blocks, whatever. Okay, so the important point here is that you never use kinetic energy initial equals kinetic energy final to solve momentum problems, or I should say collision problems. Okay, if you do, you will get the wrong answer. Okay, so beware of that. If it's a collision, momentum is king or queen or whatever. All right, let's do another example. Let's suppose we have a rock, okay, and let's suppose that it is a 40 kilogram rock, and it is traveling this way at 50 meters per second. Okay, it explodes. The rock explodes. And so this isn't really a collision. It's more of like a collision viewed in reverse, but that's fine. Okay, so collision viewed in reverse. It blows up. All right, and it breaks into 3 chunks. Okay, there's a 10 kilogram chunk here that is sent this way at 100 meters per second. There is another 10 kilogram chunk here that is sent this way at 30 meters per second. And then the remaining chunk, because none of the mass was destroyed in the explosion, okay, so there's some kind of an explosion. I'll indicate that by like this. But because none of the mass disappeared, this would be a 20 kilogram chunk. All right. And what we want to know is, what is the final velocity of the 20 kilogram chunk? Okay. So this one is a lot simpler than the last question. So we're just going to use P initial equals P final. The initial momentum is going to be just the entire rock, so it's going to be m, which is 40, times v, which is 50. The final momentum is going to consist of 3 parts. So we have the momentum of this one, which is 10 times 100. The momentum of the 20 kilogram one, which is 20 times an unknown velocity. And then the momentum of this one, which is going to be 10 times negative 30. So because this rock is going to the left, momentum is a vector, okay? So for kinetic energy, because it had that v squared, even if you were going to the left, you still had a positive kinetic energy because the negative sign was squared, okay? But for momentum, there's no v squared, and so this one just, it's headed to the left. Okay, so we can use this equation to solve for the final velocity. We have 2,000 equals 1,000 plus 20 VF minus 300. Okay. So that says that 1,300 equals 20 V final. Cancels out, and we get 65 meters per second. Is V final. So that's a positive number. So that means that that this rock is still continuing to the right. If I had solved and gotten a negative answer, then that would mean that the rock got blasted in the opposite direction. Okay. I want to do a couple of problems where momentum and energy are together. Okay. So I'm just going to do a couple of classic momentum problems that involve energy. Okay. So actually I'm going to do 2 more examples. So as an example, let's suppose we had a spring that is compressed. All right. Okay, and it's compressed by some amount x. Okay, so the amount that it is compressed is x, and there's a little block on the end of the spring that has mass m1. The spring is used to launch the block, where it then collides with m2. Okay, so it collides across with with the second mass, and they have a completely inelastic collision. And so what we want to know is what is the final velocity of the pair. Okay, so we have to do 2 things here. The first thing is we have to figure out what is the launch speed of this mass 1. And so for that, we're going to use energy. But then the mass leaves contact with the spring, okay? So you have 1/2, and then it becomes a momentum problem. So it goes from an energy problem to a momentum problem, all right? So you have 1/2 kx squared equals 1/2 m1 v squared, okay? And that tells us that the velocity of the mass 1 after it's launched is going to be square root of k over m1 times x. Okay? So then, so that's the first part of the problem. So that means that it's cruising this way with that velocity. Okay. By the way, I'm assuming that this mass 2 is initially at rest. It coasts across, it collides with M2. Okay. So because that was then a collision, we now have momentum conservation. So we're going to have initial momentum equals final momentum. So we have the initial momentum is all carried by this block. So we have m1v, okay, where v is this number right here. And that becomes m1 plus m2 v final. Okay, so you see how we could use this to solve for v final. I'm not going to carry out all the steps. All right. As another example, let's suppose we have a ramp that just goes up like this. Okay. And we have a block of mass m2 that is initially at rest. Okay. And then there's another block of mass m1 that is headed this way with speed v. They collide and they have a completely inelastic collision once again. Okay. And so immediately after the collision, they have some final velocity. Okay. And then they're going to coast up. Okay. And they'll reach a certain maximum height, y. Okay? So we want to know, what is the maximum height that it's going to reach? So, how could we do that? Well, this one is a momentum problem that becomes an energy problem. So, for the collision, we use momentum. So P initial equals P final. Okay. And so the initial momentum is only carried by M1. So we have M1V. The final momentum is carried by both of the masses. So M1 plus M2 V final. So we use that to solve for V final. Okay. Then it becomes an energy problem. Okay. So that kinetic energy that this pair of blocks have while they're stuck together becomes gravitational potential energy, and that determines how high it's going to go. So now we have kinetic energy, 1/2, and it's both the masses together, m1 plus m2 times v final squared. So this v final that was calculated right here, okay, becomes gravitational potential energy, m1 plus m2 g times y. And we could solve for y. All right. So I've just given you 2 examples of problems where momentum and energy connect with each other. So remember that for the collision part of the problem, you always use momentum conservation. And then for the other parts of the problem, you can use energy. All right. So that's my lesson for today. You guys are going to do momentum quiz 1. And as I said, I will have a double length office hours on Tuesday. Okay, see you soon. Bye.